All right. So, last thing we're going to talk about in Unit 1 is motion in two dimensions. So, all our modeling so far has been about objects that move in one dimension at a time, but we don't really need to constrain ourselves to that. So, instead, we can look at objects that are moving both in the x and y direction. And as the title implies, a special case of this will be projectiles. So, the fundamental principle here is that the x and y directions are just completely independent. So an object can be doing one thing in the x direction and another in the y, and that's fine. So x and y are totally independent. We can write the equations of motion separately for each dimension, model everything separately, and use the Pythagorean theorem if we want any sort of resultant type things here. But we'll just go ahead with an example. So an object begins moving at the origin, meaning 0, 0, at t equals 0. It has an initial velocity of 5 meters per second in the x direction. The object then experiences a uniform acceleration of 2 meters per second squared in the y direction. So, initially, I guess the motion of this object is described with an initial velocity of 5 meters per second, and then there's a uniform acceleration of 2 meters per second squared. So, the first thing we want to do is draw the object's velocity at each of the given times. So we have t equals 0, t equals 2 seconds, and t equals 4. Well, t equals 0 is easy because it's only moving in the x direction. Then, a little bit later, it'll still be moving that much in the x direction, but since it's accelerating in the y direction, we sort of have the horizontal plus the vertical, so it's going to be up and to the right. It is getting longer, although we can't show that here. And then at t equals 4 seconds, it's doing that again, right? It just keeps adding more and more vertical velocity. So that x velocity is fixed, but the velocity keeps getting more and more vertical. So that's really all I was kind of going for here, is just to show that yes, it's still moving in the x direction, but its velocity is getting bigger and bigger and bigger in the y. So it's going to approach that y axis. So let's get some expressions for everything. The horizontal velocity as a function of time, well, that one's super easy because the horizontal velocity is 5 meters per second and the acceleration is not in the x direction, so it's just going to stay 5 meters per second forever. What about the vertical velocity? Well, uniform acceleration applies, meaning we can use kinematics. So Vy is just equal to Vy0 plus Ay times t. This is our velocity time model, right? Uniform acceleration means a velocity function follows y equals mx plus b. So Vy is going to be Vy0, which is 0, plus A, which is positive 2, times t. Or we can just simplify this as Vy is equal to 2t. Because we start at 0 and gain 2 meters per second of positive y velocity every second. Now let's get some position time functions going. So, of course, technically we could start with our accelerated kinematics here, but it's actually not accelerating in the x. So we didn't actually need to do all this because if your velocity is constant, then your position is linear because the position changes by the same amount every second. So x is going to be equal to just 5t plus 0 because it starts at the origin. Because every second the object moves 5 meters horizontally. Now, what's the vertical position? Well, here we got to use the whole thing, right? Because if it's accelerating, we expect to get a quadratic. So our acceleration is positive 2. we do not have an initial velocity, and we start at the origin. So y is actually just equal to t squared. So we have functions for everything now. Calculate the speed of the object at t equals 6 seconds. So what is the speed? The speed is the magnitude of the velocity vector. So we need to figure out where the velocity is, and then Pythagorean theorem that vector, because we said it's going to become angled. Well, luckily we have functions that we can plug in to get our speed at a given time. So Vx is just equal to 5. So there's nothing to plug in there. We just have 5 meters per second. And then for Vy we said was equal to 2 times t. So that means Vy of 6 is just going to be 2 times 6, which is 12. So that means our velocity vector is going to look like this, where this is 5 meters per second and this is 12 meters per second. So what is that magnitude? Well, of course, we just got to use the Pythagorean theorem because x and y are perpendicular. So square root of sum of the squares. Has this one entered your Pythagorean triple list yet? Because this is one of my other favorites. 5, 12, 13 is actually a Pythagorean triple. So that's that. Then calculate the magnitude of the object's displacement at t equals 12 seconds. So this means how far away is it from the origin? Well, we said that x was equal to 5t. After 12 seconds, x is going to be 5 times 12 is 60. Then y, we said, is equal to t squared. So y of 12 is going to be 12 squared, which is 144. So then we can calculate the displacement because we know that the displacement is just the Pythagorean theorem. So our displacement, again, it's a pretty similar looking triangle. Where we got 60 meters this way, 144 meters this way. The right triangle, so square root of the sum of the squares. Now, of course, this works out because I wrote this, but it's not something I remember what it was. 156 meters. So let's graph everybody now. We said that the x velocity was constant, which means there was no acceleration. And the x position is just going to be linear. Then for the y, we had a constant acceleration in the y direction. We started at 0, so we just have an increasing function here, just a nice straight line. And then our y position, well, that would just be something that starts at 0, and the slopes, right? This tells you what the slopes are. The slopes are getting steeper and steeper and steeper. So that's just our classic concave up. So notice it is possible to accelerate in one dimension, but not the other. And that's usually the case we'll deal with. And when dealing with 2D motion, 90% of the time, it is this projectile motion. So anytime an object is moving horizontally and in free fall, we call it a projectile. So we have dealt with projectiles almost. We haven't considered the horizontal motion yet, but we have done so much with the vertical motion. We've done the kinematics, we've done the graphs. So now we're just adding another piece. Because the object does not care that it's moving horizontally. Gravity still does the same thing. So In this first case, we're looking at horizontal projectiles, which is basically objects sort of rolling off a shelf sort of thing. And since the motion in each dimension is independent, fall time is going to stay the same. So for these falling objects, it's just the free fall equation, 1 half gt squared. And then we can just tack on this extra thing where since the x velocity is constant, we can define the range, delta x, as the constant x velocity times time. Because the acceleration is caused by gravity, which is down. And down does not interfere at all with left and right. So we can just do distance equals speed times time in the x direction, no matter what's going on with the projectile. So our general plan here is the only thing that links x and y is time. That's all you need to know. So generally, we use free fall to get the time, and then once you have the fall time, just multiply speed and time in the x direction to get how far it lands away. A similar approach will work even for non-horizontal projectiles, where you solve for the time, then multiply to get the range. But we'll start with the horizontal case, which is an object that's moving horizontally as it's falling. So this is kind of the case here. A marble on a horizontal table rolls 1.4 meters in 0.4 seconds. The marble then rolls off the edge of the table, located 0.8 meters above the floor. First, calculate the horizontal speed of the marble. Well, it's constant. So, horizontal speed in the marble, it says it rolls 1.4 meters, or 1.2 meters in 4 seconds. So, Vx is just going to be 1.2 meters in 0.4 seconds. We have no reason to believe this is not constant, which would be 3 meters per second. Then, at each of the points shown, we're just going to draw a vector representing the velocity vector of the marble at each time. Well, it's on the table, so it's going to the right. Well, it's on the table, so it's going to the right. Going to the right. Slides off the table, goes to the right. So now what happens? Well, as the marble falls, gravity is going to speed it up, speed it up, speed it up. But there's nothing that's going to cancel that horizontal velocity. So it's going to be down right, more down, same amount right, more down, same amount right, more down, same amount right. So we see that the velocity is becoming more and more and more down, but it's still angled to the right. Notice it's very similar to what we did in this first question, right? Where there's a constant velocity in one direction and then an acceleration in a perpendicular direction, so it sort of just rotates that vector. It gets longer in one dimension, stays the same length in the other. Calculate the time the marble spends falling. Well, it's a falling marble with no initial y velocity, so that's important. We can still use free fall because yes, there's velocity, but it is not vertical, only horizontal. And the free fall equation or the kinematics are applied in the y direction. So we use the y velocity, which is 0. So we can just simplify. We can use our good friend h equals 1 half gt squared. Let's do some symbol math here. So we'd get 2h equals gt squared. So we'd get t squared equals 2h over g. So t is the square root of 2h over g. And now we can plug in. Please use g equals 10. I make all my numbers work out with it. Oh, let's see, that's 1.6 divided by 10, so 0.16, 0.4 seconds. Do I have to check that? I feel like I'm definitely right. Yeah. What's the horizontal range? Well, very easy, because horizontal velocity is constant. So delta x is just the constant Vx times the time of the fall. The marble was rolling at 3 meters per second. And it's going horizontally 3 meters per second for all 0.4 seconds of the fall, because there's nothing to change that horizontal velocity. Gravity is only vertical. So that gets 1.2 meters. Calculate the marble's vertical speed when the marble strikes the ground. Well, vertical speed, what's vertical speed? That's Vy. So let's use kinematics. because this is the speed that does change, right? Vy equals Vy0 plus AT. Doesn't matter what you want to make positive or what you want to make negative. Again, I say make acceleration positive unless if you're tossing something up, really only when it matters. So there's no initial vertical velocity, right? This is not 3 because there's no vertical speed. It just rolls off the table. It's not thrown down off the table. The acceleration is, of course, g, and it falls for 0.4 seconds. So we get 4 meters per second. Oh, look at that. That's so interesting. The horizontal velocity was 3 meters per second, and the final vertical velocity is 4 meters. Here it is. Calculate the magnitude of the marble's velocity vector when the marble strikes the ground. Well, we know the marble velocity vector is going to look like this because it's traveling down and right. And we solved and said this was just the horizontal speed, and the final vertical speed was 4 meters per second. And anytime you see those numbers, we know what's coming next if it's me that's writing this. So the magnitude of the velocity vector is just the square root of the sum of the squares. It's our favorite, our beloved, the 3, 4, 5 triangle. This is not our last 3, 4, 5 we'll see today. I went through a lot of triples already. All right, now we have a conceptual part. This is super important. This gets assessed all the time. So this is definitely a scenario to know. So suppose instead we do this sort of experiment where at the same time we launch a marble to the right and drop a marble straight down from the same height. This is commonly thought of as an experiment, a thought experiment with like a bullet, where you shoot a bullet and drop a bullet at the same time. I imagine this is like the more PG version of that, so that we're not shooting guns in the middle of physics classrooms. I don't know. So we want to compare quite a few things and just give our justification. So first, what's the magnitude of the marble's accelerations while falling? Well, keyword is right here. Marbles are falling. Which means they don't accelerate vertically or horizontally, but they will accelerate down vertically at g. Gravity doesn't care if you're moving. Gravity is just gravity. So both marbles have the same acceleration. Both marbles are falling, so they're in free fall. So their acceleration is g. That's all. That's literally it. I see a falling object. I know its acceleration is g downward. That's all. I don't have to ask any follow-up questions. What about the time each marble spends falling? Well, it's going to be the same, right? They both are dropped with no vertical velocity. They have no vertical velocity and the same acceleration. So they're going to fall the same distance in the same time. Right? Both marbles fall from the same height. Both have 0 vertical velocity at the moment of release. Same acceleration, same height to go, same time required. But what about the speed of each marble upon striking the ground? Well, if we think about what's going to happen, the dropped marble, it's going to fall, speed up, speed up, speed up, and it's going to impact vertically. But the launch marble, it's going to drop, speed up, speed up, speed up, speed up vertically as well, but it's angled because it also has some horizontal velocity. So this is something that's actually different. So the launch marble actually has a greater impact speed because both marbles are going to strike the ground at the same time with the same vertical speed, but the horizontal marble, the launched one, has a horizontal speed. So its velocity vector is a Pythagorean theorem situation, which is what I said here, right? The launched marble has 2 velocity components, so it is going to have a greater overall speed. All right, now we have some symbol work to do. We have a ball launcher that fires a projectile horizontally from a height h above the ground, and we're saying it strikes the ground a distance d away from the launch point. I'll have to talk to the art department, me, for this figure. This is a bit misleading. The d should really end like why I did that. All right, let's figure out the range of the projectile in terms of h and v0. So quite a few edits on this page, I guess. All right, so we know that the x velocity is constant. So d is just going to be the x velocity times the time it spends falling. So d is just equal to vx times t. So what is t? Right, because vx is vo in this case. So all we need is to substitute away that t. Well, we said the key here is always just use some free fall kinematics, right? Free fall says h equals 1 half gt squared. And we actually solved this before where we got t squared equals 2h over g. So t was the square root of 2h over g. So that means we can just plug in and we get d is v0 times the fall time, which we can substitute the quantity 2h over g for. And now we get our first exposure to these sort of ratio proportion questions. So the range is currently d, and we want to find the range under these conditions. So first we're going to double the launch velocity, then we're going to double the launch height. So our expression is d equals v0 times square root of 2h over g. So I call this the multiplier method, where you just put little multipliers above all the things that are changed. So here we're doubling the launch velocity. So this is a times 2. And then I'm not changing anything else, so I'm putting a times 1 there. Although I usually don't write that if it's not changing. So what happens here? Well, the v is linear, so there's nothing weird happening to this times 2. So I have a times 2 in front, and then nothing here is changing because it's all multiplied by 1. So this means that the range will double, 2d. Right, my net change would be a times 2 multiplier. And this can get a bit weird if we have square roots and squares and things. So let's look at this case. The launch height is doubled instead. So here, I'm doubling the height. So I have a multiplier of times 2. It is on the numerator, but it is under a square root. So my multiplier would be times 2, but it is under a square root, so that would be square root of 2, my multiplier times d. And notice both of these make sense that these numbers are bigger than 1 in front, right? If I have a larger horizontal speed, it's going to fall for the same time but go faster, so it goes further. And then if I double the launch height, it's going to have the same speed as originally, but it's going to spend more time falling, so larger range there. Now let's figure out the launch height we need to achieve a range of 2d. First, directly using the expression. So d equals v0 square root 2 times h over g. So what we want is d to be times 2. So what can we do to h to get out times 2? Well, notice that what we need is we need this quantity that contains h to double. And since h is under a square root, we need to ask ourselves, what do we have to square root to get out 2? Well, that means we have to multiply the h by 4. So this would be 4h. And then we can also use a qualitative argument. So how could we have reasoned this without having to do the multiplier? So it all uses the fact that we know that sort of these are our two equations. We have delta x is vx times t, and h equals 1 half gt squared. So if we want to double the range, we need to double the fall time. So we know we have to double the fall time. But double the height doesn't equal double the fall time because it's a square relationship. So we actually could figure out that since height increases quadratically with distance, we'd actually need 4 times the height to get double the fall time. So that's sort of my argument there, is that to double the range at the same speed, the fall time must double. And since height fallen increases quadratically, twice the time means 4 times the height because of that t squared. So double the time, 4 times the height. That's kind of tricky. I don't know how qualitative this really is, but these are the sort of the things I want you to think about, is how can we do things without plug and chug symbols all day? There's also many ways to do this problem that aren't like this with the multipliers, but multipliers are so much better, especially for AP. All right, that's it for horizontal. Now let's launch at an angle. So, same idea. If we launch a projectile at an angle, x and y are independent. Gravity only affects the vertical. If we find the total time in the air, we can multiply that by our x velocity to get the range. And that's essentially it. So what we will do in this class, we're going to focus on what are called ground to ground launches. We start on the ground, we end on the ground. There's a lot of nice things there. It makes sure that we have zero net displacement. It makes sure that we can perfectly cut our picture in half at the midpoint. The time up equals the time down. And most importantly for me, in my love of mathematical elegance, we don't have to use the quadratic formula if we have these nice ground to ground launches. So once again, the acceleration is just g down, so it only affects the vertical motion. And since we are launching up in this case, this is the one time where I like to make g a negative quantity, because we're moving up and then down, so it just helps manage everything. So notice here that this would be like our dot diagram, where we're launched up and to the right, and then a little bit later we're slower because g is fighting us. We're even slower. We stop only vertically at the top, right? Because gravity doesn't tell the right vector to become left. Gravity just tells the up vector to become a down vector. And then the pattern is symmetric and repeats on the way down. So it is actually really important to know what happens at the top. This is asked on like every test ever. The velocity is not zero. It is only the y velocity that's zero. It still moves horizontally. Because if it wasn't, then it would just fall straight down, right? If it stopped at the top, it would just fall straight down, and that definitely doesn't happen. So it stops vertically, but not horizontally. And it definitely doesn't stop accelerating, because acceleration is due to gravity. So does gravity ask a projectile, hey, are you at the top yet? And then decide to stop? Ask and just stop acting? No, that's not how gravity works. So acceleration is always g at every single point. G, 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 G. So that's kind of what we have going on here. Definitely remember this dot diagram for the velocities. So we see the vertical velocities change and are mirrored, but the axes don't. All right, we're going to do a minimal trig one here. A ball is kicked at this velocity, where its horizontal velocity is 15 meters per second and its vertical is 30. We want to draw quantitatively accurate vectors showing the velocity components at each second and the acceleration. So I actually think it's best just to start with acceleration, because what is acceleration? Well, this is in free fall. This is free fall. So A equals G down. G, 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 etc. The acceleration is constant and G at all points. So what's a consequence of that? I probably should have flipped these. It's okay. What are the horizontal and vertical velocity components after each second? Well, the easy one is the x velocity, right? Because we said gravity does not care. Gravity does not care what is happening horizontally. So this is our initial launch speed. 1 second later, gravity doesn't care you're moving horizontally. 2 seconds later, gravity doesn't care. 3 seconds, gravity doesn't care. So at every single point, you can automatically just fill in at 15 meters per second. Because our acceleration is purely vertical. And now we will deal with the vertical. So every second we add our vector 10 meters per second down, or negative 10, if you will. So 30, positive 30 plus negative 10 would be 20. Positive 20 plus negative 10 is 10. Positive 10 plus negative 10 is 0. Then we get negative 10. No, I shouldn't write negative 10. Directions already encoded. 10, then 20, then 30. So notice we get our nice expected mirror pattern that we see in the figure above. So we count by g's, or count by negative 10s vertically, and we count by nothings horizontally, because gravity does not act horizontally. Let's calculate everything. What is the time that the ball spends in the air? Oh, really challenging. We don't start at 1, right? All timers start at 0. Really challenging. What's the time in the air? 1, 2, 3, 4, 5, 6. 6 seconds. I just counted the dots. Do I ask this? No, I didn't actually ask this. You could have actually figured this out using, there's several ways of doing it. You could pick your favorite kinematics. I'm not going to do it now because I'll show you how to do it in the next one where we don't have a dot diagram. What's the horizontal range? Well, that's super easy because delta x is just vx times t, because my x velocity doesn't change. So I go 15 meters per second for 6 seconds. Ooh, that's the hardest part. What is 15 times 6? That's 90. 90 meters. Right? It's going 15 meters per second its whole flight. So it goes 15 meters 6 times. Now let's find the maximum height a couple different ways. So first we're going to use the time-independent kinematics in the vertical direction. So when does it reach max height? Well, it reaches max height right here. So we're going to look at this segment of the motion. Might help actually to look here, because we have our velocities. So we can see that the y velocity starts at 30 and ends at 0 at that point. So we could use, it says use the time-independent kinematics, which is this one. So at the top, the velocity is 0. Our initial velocity is 30. Our acceleration is 10 meters per second down. If we consider that upward velocity to be positive, our acceleration has to be negative because they're going to fight each other. Times delta y would just be this h. So we would get 900 equals 20 times h. So h would be 45 meters. Again, we're going to get into the habit of just not doing things with numbers until the end, but kinematics is sort of my exception, where I think it's reasonable just to plug in pretty early in these. And then we can also use symmetry and free fall, apparently. So this seems kind of odd because we said h equals 1/2 gt squared only applies when there's no initial velocity. But if we're clever, we could say, wait a second, what if we just pretend our motion starts at the top? Because I have a falling object now, because it does not have velocity at the top in the y direction. So this equation always works if we say the t represents t of the fall. So if it spends 6 seconds in the air, then it must have been rising for 3 seconds and falling for 3 seconds by symmetry. So we get 5 times 9, which is definitely 45 meters. So works out. I like that. I like this as a little clever second approach. There's a million ways to find max height, and I thought this is an interesting way to show you these. You could have also used other kinematics equations, and it would also give you that. So it's less common for you to be given the components. Instead, you're actually usually given the launch velocity in magnitude direction form or polar form, where we tell you the launch velocity and the launch angle. And as soon as you have that, you just need to know I need to instantly break this into the X and Y components. Because we don't do kinematics at an angle, we only do kinematics in X and Y. So as soon as you see an angled projectile, you got to break it up into X's and Y's. And this is the only type of projectile you'll see launched in this class where it's horizontally this way. So it is always the case that the X component is going to touch the side. So Vx is VO cosine theta. That's the one that doesn't change. And then the one that does change is your initial Y velocity, V0 sine theta. So when you're modeling the motion of the projectile, we can say that its X velocity is just going to be, its X position is just the speed it goes every second in that direction times the time. Then the Y, we have to use our accelerated kinematics. And since we love to deal with just ground to ground launches in this class, we will never have this Y0 term because we're always going to say we start on the ground. If we didn't, it would be quadratic formula time, and that is not pretty. So that's going to be our setup, is always recover these. So as soon as you break the launch velocity apart, you will never need that launch velocity again. You'll only use the components. And of course, we do the negative here so that we get that downward opening parabola we expect. And you'll always get a nice, factorable, symmetric quadratic. All right. Shout outs to me for this lovely rocket. At t equals 0, model rocket is launched from the ground with an initial velocity of 50 meters per second at an angle of 37 degrees above the horizontal. Whatever could the components be? So we want to first calculate the vertical and horizontal components of the initial velocity. So we could call it Vx0, but it's just sort of Vx because the x velocity doesn't change, and then the y velocity will. So remember, using our definitions of what the trig functions do, is our definition of what the trig functions do is multiplying by cosine theta gives the component that touches the angle. And we've always said that for projectiles, the launch velocity times cosine of the angle is going to give the x velocity, and sine multiplied by the launch velocity is going to give the initial y velocity. That's the one that will change. And how do I know this is right? Well, cosine is associated with adjacent. So the 37 degrees touches the x component side. So I know this will be cosine. And the sine 37 is associated with the vertical side because the 37 degrees does not touch the y velocity side. And I said, what could we possibly think the velocities are? Well, this is the 345. And while I'm writing this out, remember that if your angle is flat, it's more horizontal. And if your angle is if your angle is more vertical, that means you have a higher vertical component. So if your angle is less than 45 degrees, it means the component touching the angle will be bigger, which is usually the x. If you have a shallower angle, the x component will be bigger, and if you have a steeper angle, the y component will be. So I actually know that this will be the 4 side in the x, and the y will be the 3 side, because I know that 37 degrees is more horizontal than vertical. So that's where the long leg in that triangle goes. Now, of course, just use your freaking calculator, right? Calc for slang. This should be pretty close. So if I do 50 cos 37, yeah, it's 39.9. So be on the lookout. AP loves these angles. If possible, we will always use these. Like you get nothing for making these garbage numbers. All right, so now let's do our position functions. So for x of t, well, x is just linear, right? I go the same distance every second. So that would just be vx times t. which means that x is just equal to 40 times t. So every second, we get 40 meters further away. Now, what about y? So y, we have to use the whole kinematics. I really don't even need to write this, but because we're always dealing with ground-to-ground launches. So y would be equal to negative 1/2 times g is 10, so negative 5 t squared, plus our vertical velocity component is 30t plus 0. So those would be our functions that model x and y. Notice the 50 is gone. The initial launch velocity is 50, and that did not show up anywhere. Our first goal is to just eliminate that launch velocity. It is not important. We need to split it into components to do anything meaningful. Let's calculate the airtime of the rocket using the y of t expression. Then we'll use vertical velocity kinematics and some sort of half-time symmetry there. All right, so let's use our expression for y of t. So we said that the height of the rocket, y, as a function of time, is negative 5t squared plus 30t. So what does it mean for the rocket to hit the ground? Well, if the rocket hits the ground, or the time spent in the air, the rocket has returned to Earth. So the y is 0. And again, another reason we do ground-to-ground launches is because now we can factor pretty easily. So everybody has a negative 5t in it. We'll pull out. Do I want to do that? Yeah, because then I get t and then minus 6. So when does the rocket hit the ground? Well, the rocket's on the ground when 5t is equal to 0, so that means t is 0. Okay, that's pretty obvious. That doesn't tell me anything. But the rocket also hits the ground when t minus 6 is 0, so t equals 6 seconds. There's nothing wrong with the t equals 0 solution. Like, it is valid. It's just not the one that we're interested in. Let's show we get the same thing if we just did kinematics. So what does that mean? Well, we just use what we call the half-time symmetry. So if we want to find the time, we could also say, wait a second, we know that it is going to... We know that at the top of the trajectory, there's no y velocity, but we launched upwards at 30 meters per second. So if we do this, we can use Vy equals Vy0 plus At. So we're 0 at the top. We were launched upwards at 30, and we have a constant net acceleration down of negative 10. Or we have a constant acceleration of negative 10 meters per second because it's 10 meters per second down. So we see that t at the halfway mark is 3 seconds. So this means the total time is just going to be 3 times 2, which is equal to 6 seconds. So that's another way at it, is if we just say, well, this is going to be exactly half the time. Takes the projectile half the time to get to the top and half the time to get to the bottom. So if we solve for the half time, we could double it and get the full time. Now let's find the range. So the range, always super straightforward. It's just Vx times t. Our x velocity was 40 meters per second and 6 seconds, so 240. All right, now we'll give you a little bit different piece of info where we have a golf ball is hit from the ground, spends 4 seconds in the air, and lands 192 meters away. We want horizontal speed, we want vertical speed, and we want the launch velocity in polar form, meaning we want the magnitude and direction. So the horizontal launch speed will always be the easy one. X velocity is constant, so I just take change in x over change in t. I went 192 meters in 4 seconds. And I get something that I'm weak and need a calculator for. I'm going to guess it's 48. Absolutely. I would just hate to have to refilm because I'd get too confident in my mental math skills. All right, calculate the vertical launch speed of the golf ball, and it says use halftime symmetry. So why did I say use the halftime symmetry? Well, what we know is that we spend 4 seconds in the air. This means 2 seconds takes 2 seconds to reach the max height. And at that point, there's zero vertical velocity. Now, at this point, you could just count, right? Well, after 2 seconds, I've reached the max height, so 10 had to stop me twice, so it's 20. But of course, we could just write Vy equals Vy0 plus At. So we'd have zero velocity after our negative 10 meters per second of acceleration stop us for 2 seconds. So this means Vy0 is positive 20 meters per second. Now let's calculate the launch velocity of the golf ball in polar form. All right, so we have 48 meters per second and 20 meters per second. So this would be our velocity vector. So we will be interested in how long this is, and we will be interested in this angle. So of course, pretty easy. We know how to get the launch velocity magnitude. It's just the square root of the sum of the squares. Oh, what is this? Is this a new Pythagorean triple? This is a decimal. I'm going to be very sad. 52. Wow. Thank you, me from the past. And then what is theta? So whenever we're solving for the angle theta, we're usually using tangent, right? Because tan theta is equal to the opposite side divided by the adjacent side. That's not my answer. I want what's inside the tangent. I want theta, so I have to undo the tangent. So theta would be inverse tangent of 20 over 48. And it's impossible to get both of these things to work out nice, so I know this will be a decimal that I need my calculator for. 22.6 degrees. So our launch velocity would be 52 meters per second at 22.6 degrees above the horizontal. It's how we say that. But again, my picture is pretty clear in what we mean. So that's a pretty interesting one. So now we're going to get rid of the numbers and do stuff with symbols. So there's quite a few things we could want with the general case. These are not formulas that are necessarily worth knowing or memorizing, but I find them useful kind of for shortcuts. Maybe more for mechanics than AP1. But in general, these are some results that we're going to prove in a little bit. So time in the air of a ground-to-ground angled projectile is that. Max height of an angled projectile is that. Horizontal range of an angled projectile is that. So we'll try to prove each of these a bit later. So we're just kind of going through some properties here. So if this is our launch velocity, the horizontal is V0 cosine theta, and the vertical is V0 sine theta. So what this means is that the air time goes up with vertical components, and the max height goes up with vertical component as well. And that should make sense, because as we launch a projectile, what causes it to stop and turn around? Gravity. So the more juice you give the projectile in the vertical direction, the longer it takes gravity to stop it, so the longer it takes to hit the ground. And the range equation is a bit harder to think about what's happening here. So I think I'll just kind of spoil this for you. Uh, Sine is maximized when the angle inside is 90 degrees, right? Because the most vertical you could be is 90 degrees. So sine of 2 theta is maximized when theta is 45 degrees. So this is a fact that we should memorize, is that the maximum horizontal range for a ground-to-ground launch is achieved at 45 degrees. And as a consequence of this, there's a couple things you can look at. So T air and H max are very straightforward. The more vertical the angle you launch from, the larger those quantities are. Because you spend more time in the air, so you go higher. Now for the range, 45 degrees is the best, and then it's symmetric about that point. So if you actually graph what this looks like, we should call this delta x. You get something that looks like this, where this peak is right at 45 degrees, and it's symmetric. So if your angles are the same distance from 45, they yield the same range. So why this works is because the distance delta x is vx times t. So you can't just put all your eggs in the T air basket and get a super long air time, because then you have no velocity left in the x direction. And you can't put all your velocity in the x direction because then you have no time in the air. So to get a long range, you have to somehow balance the x and y velocities. And when are the x and y velocities perfectly balanced? At 45 degrees. So that's my little explanation of why 45 degrees is the maximizer, because you get both time in the air and horizontal speed, which are the two factors. Because if you totally sell out to one of them, the other gets basically to zero. And also, as a consequence of this, if angles are complementary, they also yield the same range. Because complementary angles are actually the same distance from 45 as one another. So, for example, 50 and 40 are going to yield the same range because they are 5 degrees apart from 45 each. Notice they're also complementary. So this is a great ranking task. Object is fired at all of these angles. The launch velocity is the same. We're just determining where to distribute it. So do I want it 30, 45, 60, or 90? So we're going to rank airtime, H max, horizontal range, and then we got something else. So we already said that for time in the air, you get more time in the air, the more vertical you launch. We already went through that argument, because the time in the air is just double the time it takes to stop at the peak. So if you give it more vertical velocity, the object is going to take longer to stop and thus longer to hit the ground. So the larger the vertical components, the larger time in the air. And as a consequence, the heights will follow the same pattern. Because the faster you're launched up, the longer it takes to stop, so the higher you go. Because you're launched with a bigger speed for the same acceleration, so you go higher. Then for the range. So the range, we can definitely do a couple things here first. So first of all, we said that 45 degrees is absolutely the winner for horizontal range. This is just a fact. Then, if we also look at this, we also can definitely pick the loser. Because scenario 4, if I'm launching it straight up, and then it falls straight down, there is no horizontal velocity. So it has gone absolutely nowhere. So 4 is the loser. And then we got to figure out what's happening with 3 and 4. Sorry, 2, sorry. I cannot read. 2 and 1 and 3. Whew, it's tricky. So if we look back here in our facts, we said the range depends on how close you are to 45 degrees. And if we look at 30, 30 degrees is equal to 45 degrees minus 15 degrees. And 60 degrees is equal to 45 degrees plus 15 degrees. So notice both of these launch angles are the same distance from 45. They are both equally close to the maximizer. Or you could use the other property and say 30 plus 60 equals 90. They are complementary, which yield the same range. Either way, we have a tie of 1 and 3. So that's the tricky launch there. So the range of a ground-to-ground launch is maximum at 45. Horizontal range is greater when the launch angle is closer to 45, with complementary angles yielding the same range. Now we have scenarios 5 and 6, where we launch from the ground versus launch from a cliff at the same angle and same speed. What would be the range comparison in this case? Well, what is range? Well, the range is definitely just Vx times t. And if we're launching from the same angle, we know Vx will be the same for each of these. So we just got to look at t air. So we know that scenario 5 is going to have some path like this. And scenario 6 would also have that same path until it reaches sort of the ground spot. So scenario 6 has to do everything scenario 5 does, and then it keeps falling. So there's extra time in the air spent in scenario 6. So there's extra range. In scenario 6, the path is the same as the path in 5 with extra stuff. So that's kind of the extent of what I imagine you'd see with like a non-ground to ground launch. If you actually wanted to solve for the time in the air, I would honestly just use Desmos, because it would be a quadratic formula situation most likely. All right, last exercise is we will prove all of those boxed formulas. All right, general case, projectiles launched at an angle v0 above the horizontal. Launched at velocity v0, angle is theta. Determine expressions for the horizontal and vertical positions of the object as a function of time. Well, of course, we know that u are v0 cosine theta and u are v0 sine theta. It's just our standard angle. Go over here. We know that x follows vx times t. So we'd have v cosine theta times t would be our x as a function of time. And then we know that y follows the typical free fall model. And this is not numeric, so we're not going to plug in 10 for g here. It is g. And it is a ground-to-ground launch, so we can get rid of the initial height term, because we're starting from the ground. So y would be equal to negative 1/2 gt squared plus vy, no, not vy, v0 sine theta times t. So that would be our expression for y. So all we did is we replaced the initial velocity terms with their components. So notice v0 is actually gone. It's the components that we use. All right, how do we find the time in the air? Well, we know that it hits the ground when y equals 0. So we just set negative 1/2 gt squared plus v0 sine theta times t equal to 0. This looks scary, but we can definitely just do some factoring. So let's pull out. We pull out from everybody. We can pull out a t from everybody. And we would get negative g over 2t plus v0 sine theta is equal to 0. So one way we could get this to be 0 is just having t equals 0. That's not helpful though. So we're looking at when is this object equal to 0. So negative g over 2t plus v0 sine theta equals 0. So I would get g over 2t is equal to v0 sine theta, or t is equal to, multiply by 2, divide by g, 2v0 sine theta over g. And if we go up and check, 2v0 sine theta over g, that's exactly what we wanted. All right, verify the maximum height. You can kind of pick your poison here on which way you want to find the max height. One way you could do it is you could just plug in half of this into h equals 1/2 gt squared. That's actually a pretty good idea. I'll show you the more traditional way, and then we'll check it. So we could use like the half-time symmetry idea. So Vy equals Vy0 squared. All right. Vy squared equals Vy0 squared plus 2ay delta y. At the top, there is 0 y velocity. Our initial velocity is v0 sine theta in the y direction. Our acceleration would be g down, and h would be our height. So we'd get 2gh is equal to v0 sine theta all squared. So h would be equal to that expression divided by 2g. And that works. Definitely what we expected. Now, we could also have done this just by saying h equals 1/2 gt of the fall squared, which is 1/2 g. And if the whole air time was this, the fall time would be that divided by 2, so get rid of the 2. And that actually does work because we get a g squared in the denominator, so that gets one of those, and the 1/2 can live in the denominator as a 2. It does work. And then lastly, we'll get range. So this is the key with the range formula that gets people, is that you need a kind of niche trig identity if you're not fresh on your pre-calc. This is like the only trig identity I've ever seen in this class, but we need this. So what is range? Well, range is easy. Range will always be easy. It's just Vx times t. Vx was V0 cosine theta, and t would be that air time that we found earlier. So we have two factors of V0, so that makes a V0 squared. Then we get a sine theta and a cosine theta on top and a g on the bottom. And it says that our key identity is 2 sine theta cosine theta equals sine 2 theta. So we can just associate that 2 with the trig functions, and that will give us the result we want, because this is just what our trig identity says is sine 2 theta. So we can get delta x is equal to v0 squared sine 2 theta g. This is more of like a multiple choice shortcut, I guess, if you know this. But the real thing that pops out of this is knowing the 45 degrees idea. But all of these are helpful to solve general projectiles. But we could have just derived this once and then plugged in stuff from the other questions to make it work, which is why we do things symbolically versus random numbers. All right, that is Unit 1.